Alright, the first example we're going to look at here is an application of Bernoulli's equation. What you'll see on the left-hand side here is a mercury barometer. This is one you won't see in the lab because it has an open bottom, basically dish of liquid mercury, which is, against our health and safety guidelines. But the idea here is there is a pressure of the atmosphere that is exerted downwards, right, onto the bottom of the mercury. And so there's some kind of atmospheric pressure here. And the idea is this atmospheric pressure causes this column of mercury to move upwards. So likewise, there is a pressure on point A down here at the bottom due to the column of mercury. And the idea for this system is, depending on the change in height, you can determine exactly how much atmospheric pressure is present here. Keep in mind the top here is actually empty, right? So there's no gas or anything in here, or as close to it as you can reasonably get. Now, the idea here is you measure this change in height to be 25 centimeters, and your goal is to figure out what the atmospheric pressure is. All right, so this is what we're going to try to do here. All right, so to start this off, we're going to take a look at Bernoulli's equation here. Now, for Bernoulli's equation here, what you want to do is you want to compare two different points. Right, that's effectively your goal here. So the 2 points that we're going to pick, it really is up to you which one you actually want to use here. But the two I'm going to pick is I'm going to pick this top layer here, and I'm going to pick, secondly, this bottom point A here. Now, the nice thing about this system is what you'll notice is none of this stuff moves, right? There's no flow here, it just sits here. What that means is you can immediately get rid of the kinetic energy associated term there, because the velocity or the speed of the thing at both the top and the bottom part that we're going to pick, the red line and the blue line, are zero. So you can just get rid of them altogether. Now, with that being said, right, what we want to do here is we want to figure out what the pressure difference is between these 2 points. Now, with that being said, we got to compare them. So we're going to start here with the one at the top. Now, with the one at the top, right, we'll use this as the unprimed side. There's no pressure in this mercury bulb that's pushing down on the mercury beneath it. So at this top point here, there is no pressure. And so we can eliminate those two terms right away. At the bottom point, there is a pressure, and that is actually going to be our atmospheric pressure. Because as the atmospheric pressure pushes down on this side, it's going to push up on this side. And these two forces are balanced. So the pressure at this particular point is actually what we're looking for. Now, with that being said, we only have a couple of terms left here. So what we can do is we can rearrange this. So at the end of the day, what the easiest way to do this is just simply to move the second gravitational term over to the other side. If you do so, you will get rho times the acceleration due to gravity times the height at the red point minus the height at the blue point is equal to our atmospheric pressure. Now, when it comes to filling this in, we can fill this in quite easily. The difference in height between these 2 points is the 25 centimeters that we've been provided with, or alternatively 0.25 meters. As for g, in this particular equation, g is just a short form for the magnitude of the acceleration due to gravity, which is 9.8 meters per second squared. And lastly, we need the density rho. Now in this case, since we're dealing with a change in height of mercury, we're going to need the density of mercury. And this is one of the things that you'll be provided with or will be told explicitly. Here, the density of mercury, if you look it up in a table, is about 13,593 kilograms per cubic meter. Cubic meter is actually like a lot of mercury, which is why this number is so large. So what we can do here is we can actually put this all together. So what we're going to do here is for our atmospheric pressure, we're simply going to take our density, we're going to multiply it by the acceleration due to gravity, and we're going to multiply it by the change in height, all in SI units. And when these are in SI units, we will get the SI unit of pressure, or a Pascal, or a Newton per square meter out of it. Now, you can multiply these all together, and if you do so, you get 3.3 times 10 to the fourth pascals, and if you want, you can convert this to about 33.3 kilopascals, or if you're a fan of millimeters of mercury, 250 millimeters of mercury, like so. So the idea here is you're going to be comparing two situations, examining whether or not there are velocities, heights, and pressures here. And one of the tricks is you can often group the two height terms together in order to get a change in height. And this is fairly similar to what we did when we were talking about changes in energy.